So let's do problem. What did we say? 15100. Okay, so the system is at rest. So what does that mean? V initial equal omega initial equal to 0. In the position shown with the 12th color A resting on the spring. Okay. All right. Let's see. K. I'm just doing the figure. A is attached to a string. Okay, so let's see. I put in the distances now. 3 feet, 2 feet. Okay, so K equals to 20 pounds per foot. When a constant force F of 30 pounds force applied to the cable, what is the velocity of the collar when it has risen? So let's say when H equal 1 foot. Okay, so this is my figure basically, okay? Hope yours is better. A bit of a task. So, but I'll give you the basic equation. So remember, all this chapter is about work and energy, no? Principle of work energy. So if you remember, first thing you need to do a figure. All right, so let's do. So I know, and this is the part that is not very clear, it's the part that you need to do the figure over here. So it's going to be a bit strange on the figure. So figure, I will kind of redo something similar over here as you have. Maybe a little bit different here, but I'm just doing this. So basically, what do we have as forces? I have a force F over here. What are the other forces being applied over here? The weight of the collar, no? And then what else? The spring, as this is moving up, the spring will also try to do a force to pull you down, no? Yes. And this will be whatever you want to call the distance up, X, Y. Let's say this is, let's just say S. Is that okay? That way it's better. Okay, S. And then this will be moving a distance what? A distance, if you want, let's say over here, but H. Okay, so that this will become like this. I mean, you need to do some type of figure, no? What should be step 2? So basically it will be the same thing as with summation of forces equals to M summation of moments. So let's say work and energy equation. Which is what?
Yes, was the
All right, so this is work done by linear by forces, work done by moments, change in kinetic energy due to translation, plus change in kinetic energy due to rotation, no? So I'm going to help you a little bit and then I'm going to let you work a little bit on your own, okay? So as I get you started. Now, out of this problem, what type of motion is the car going to have?
translation.
Translation, okay? So basically this will mean this is zero, no? Is it any moment being applied? So this is zero. The system is initially at rest. So this is zero. So basically here what you're gonna have is summation of the forces ds would be equal to 1/2 mv squared, which is what you need to find, no? So I mean, this is a classic problem. What are the two forces that you have? One will be the gravitational force, mg. The other one will be the spring, no? So go ahead and do it. Stop just copying. I want you to do a little bit on your own. I give you 5 minutes. Is that enough time? 7 minutes, okay? To 37. Not the solution, but on the part of the statements. So basically, this is where we are, okay? So what are the three forces that we have over here? We have mg. What are the three forces that we have? The other forces will be the weight, no? mg, the spring, and the force F of 30 pounds. Okay, so let's start maybe by, we're going to leave the spring for the end because that's the only thing that might be confusing. So let's say letter A. Work done by weight. Okay, so if you think about it, I do a little figure here if you want. This is where you initially. This is what it moves next, okay? So we have over here what is our expression is summation of force is summation of forces ds. So in this case, what is the value of the force? Will be negative mg. If you want, what would be the force? Positive work is when if you push something, the force and the direction of the movements are in the same direction, no? In this case, the force is going to be opposite to the direction. So this means it's negative work if you want, but you can just look at it here, mgh. And now if I do here ds should be integrated between what? 0 and h, which is the 1 foot, okay? So this is basically just going to give you minus mgh. If you think about it, this is the expression for the potential energy, no? Okay. Now, B, let's say at the work done by force F. So here, what do we have? We have our system again over here. That is going through the pulley. What was this one? 2 and 3. Okay, so how much is the force F going to move? Is it going to move the 1 foot?
It doesn't really fall, does it?
What I mean, doesn't move? Is the one that makes move, everything moves. The thing that makes this move up is what? Is this force?
Right.
Okay.
Wow, yeah, same. So,
What would be the value?
1 foot in this case,
1/3?
1 foot.
Why?
Because we want the velocity.
So what about the string here? So this is 1 foot as well? Correct. So you want to call this one, let's say what, S initial, okay? And let's call this one S final. So what should be S initial? So from figure. S initial should be equal to what? I mean, basic trigonometry, no? So 4 plus 9, 13, so whatever is square root of 13. So basically what we're doing here is looking at the right triangle where you are over here. 3, 2, S initial, whatever that is. And S final will be what? So you will have what? You will have 2 over here, no? 2 over here and 2 over here. Is that correct? So S final should be what? That will be square root of 8. So how much is really going to move this? I mean, I can put it here if you want, but you can do it different. But if we look at the equation here, so let's say I write down the equation here: summation of forces ds for this one. This would be equal to what? F times ds, no? Okay. Is the force moving in the same direction as the string is being pulled? Yes. So that means that the work here is positive or negative? Positive. And what should be the limits of integration here should be S initial, S final. So if you look about it, this would be equal to what? F S final minus S initial, whatever that is. Okay. Square root of 13 minus square root of 8. How much is it? 0.777. So 0.777. Okay, go and check. F, no? Any question? And the one that I think is the confusing one is the last one. That's why I leave it for last. Because I think I have both interpretations, can have 2 interpretations. And what should be the last one? Work done by spring, correct? Force if you want. Okay, so personally, yes.
So the area shows their scrolls at 13 quadrant.
In here?
No, and the lowest one. Where you get.
Oh, okay.
Should
Should be what?
swap is the rear page is 5.
Oh, okay, I mean, I wasn't paying attention. So should be swapped. So yeah, so square root of 8 minus square root of 13. But you still need, it's positive, no? So you need to take the magnitude.
You take the magnitude.
Yeah, take the magnitude because F is on the same direction as the deformation. That's probably why I put it on the other way. So does that answer your question as well at the back? It should be, I mean, I put this, but really it should be square root of 13 minus square root of 8. Or you put square root of 8. I mean, do you understand this part or not?
Yes.
Work needs to be positive, no? So good questions. So now in this part, let's decide about something. That way we can just solve it one way or the other, okay? I don't care about the solution of the book. In this case, do you want to assume that the spring is unstretched at the beginning, or do you want to assume that is compressed due to the? They don't say it, but
You tell us the symbol is type of compress.
I mean that's what they do on the solution. Not to assume, you can calculate it, but I mean yes, ask. Okay, so let's find. Okay, so let's do the way they do. Okay, so initially this spring, because of the initial weight of this, when it's at rest, this spring is going to be compressed. No. Yes,
Yes.
due to its weight. Okay, so let's do that first then. So you want, let's say, initially. Spring is compressed due to the weight of the color. I think that's what it is here. They call it this one. So basically you have here, this is the color and this is the spring, no? So how much is it going to be compressed? So you have mg, force of the spring is going to try to do what? Counter-reacted, no? So if you do here summation of forces on the S direction equal to 0, what do you have? So minus mg plus, okay, let's say S initial will be equal to 0. So we can solve for S initial will be equal to what? Mg divided by K. So let's say that initially this is compressed, whatever that value is. Can you give me a value? Maybe that might be
19.31, that's like
how much?
19.31, something like that.
Well, let's look at the values. What was W? So it's 20.
It's 12. Well, we get more.
Oh, the weight. No, the weight. How much is the weight? I don't have the weight.
Is that the weight?
I don't have the weight on this. So let's see how much is the weight. Weight is 12. So I forgot to put this stuff. So 12 pounds times. Be careful here. 32.2 now. It's in feet per second. Oh, this is the weight. Okay.
Yeah, that's the weight, not the mass.
So this is so do 12 divided by 32.2 basically.
It's the same thing.
12 divided by 20.
Yeah.
0.6. Yeah, sorry for that. I was doing. So it's 12 divided by 20. Let me put it right here. That way it's clear what we're doing. 12 divided by 20. And you say it's 0.6? Okay. So that's a question. So now is he moving 1 foot from that position or is moving from? So from that position is moving 1 foot. So we can say that now S final is 1 inch. 1 foot, I mean. 1 foot. Okay. So and say over here and so we can write down now. I mean, this generally this part we assume the spring is at rest initially, but So basically at the end, what we have summation of forces, ds. So this time, a spring, okay? A spring is going to do positive work and negative work. If you compress a spring, the spring is going to try to do what? Push back. If you try to stretch it, on the opposite direction. So the work done by the spring, no matter what, is always going to be what? Positive or negative?
It's constant because it's in the same direction. It's
If you pull the spring to the right, what is the spring going to try to do? Go to the left. If you pull the spring to the, if you compress it, it's going to try to push out. If you stretch it, it's going to try to pull it. So no matter what, the work done by a spring is negative. No, it's always going to act against the deformation. Yes?
But in this case, you can put us and go under. Isn't the spring in this case trying to move
This
you
gets
in the
blocked
direction?
because
you're
compressing
compressing
out against the movement. Well,
For part of it is going to be positive.
If you're compressed at 0.6, you're going to 1, and that's in the direction the motion of the block. So isn't it positive in this case?
Okay, so good observation. Okay, so basically, but we're going to put it into the equation. So let's say here the work, let's say here will be Ks ds. Okay, so let me just over here, this is going to be as initial as final. Let me put negative because I want to really show you that there is always this. Okay, so really the work done by spring, if you remember that from physics, what is the kinetic, the potential energy of a spring?
1/2
1/2 kx squared. So let's over here will be 1/2 kx squared between S initial and S final. So maybe now we can play with this. I think you had a very good point over here. So let's say will be minus 1/2 k. So all right, let me write this down and see if we can make it work, okay? If we do this, this is equal to this, no? Okay, so maybe we can do a figure here. Maybe this over here. So we can say here this is, as you mentioned, here is compress as initial. No? So in this case, you see, if it's compressed as initial, we have negative and negative. This will become positive. Now we need to decide what's going to be SF. So SF is just the 0.4 then, or is 1?
Final would be 1. I think that's what we.
But if we do that way, you will say only be negative 4.4. Yeah, but it's I mean, guys, do you understand here the issue or not? Okay, so whatever you, I mean, so okay, so we can say, but I think if we need it, so we can say that all this stuff here is 1 foot, no? Then this part over here that will be as final, then will be what?
0.4 off of the
0.4 because this is 0.6, no? So basically we can say here that S final is 0.4 as initial is 0.6. Whatever that value is.
Would you still say that last final is 1 foot?
But here we're doing 1 foot is moving. You are just think about the work. What is the work? Just like you said, the work done during this spring here will be positive, which will have negative, and if this then will be 4.4 will be negative. Correct. So basically, let's say combining everything. And I'm going to leave it symbolic. If you want to do the calculations, what we have? We have summation of forces ds equal to 1/2 mv squared. So what do we have? We have the force done by the weight. We have minus mgh. No, the first. Okay, A. Now work done by force P. We had that one to be plus 0.777 F. Now we're gonna have minus 1/2 K, and I'm gonna put values over here so that we differentiate with the 0.6 squared minus 0.4 squared will be equal to what? 1/2 mv squared. So, I mean, if you want, I'm going to write it down, but I'm not going to do the calculations. You will have V will be equal to what? 2 divided by M times all this stuff over here minus mgh plus 0.777 F minus 1/2 K of 0.6 squared minus 0.4 squared. And you will be taking the square root of all this stuff. Okay, you know I don't like to do calculations because I think if you're going to study on this, I think it's easier by looking at symbols, no? Yes.
So why is it again for the work done by the springs, you denoted it as negative?
Okay, because basically what we're discussing is that initially this is the spring, okay? If you put weight on top, it's going to be compressed. It's being compressed how much? 0.6. Okay, so now the work done by the spring until it gets back to its unstretched position, is that going to be positive or negative work? The force is going to be on the same direction as the deformation, no? So for example, let's say you have a spring, you compress it. Now, what is the spring going to try to do? It's going to try to make it go up, no? Yes? So it's going to try to make it go up until it gets to this unstretched position. So that position will be what? 0.6. Did I confuse? Oh, I put this reverse, no?
Yeah, exactly.
So 0.4 minus 0.6. So basically, what does that mean? That for that 0.6, the distance that is stretched, the work is going to be positive. Does that make sense or not?
Yeah.
So you have negative will give you positive. And then after the position that is unstretched, now that the spring is unstretched, if you keep pulling, what is the spring going to try to do? It's going to try to go against the deformation. And in that case, will be for the restant 0.4, it will be negative.
Okay.
Does that answer your question? No?
Yep. Yeah. Now that we switched.
That's what we. Correct. Correct. So if you want this term over here, negative will be the part that is compressed and it goes to the equilibrium position. And this part is when it goes from the equilibrium to the stretch position.
When the V equals. So 0.6 right.
So here I reverse this one again. Here 0.4 minus 0.6. I mean, conceptually, did you understand the problem? Personally, I will have said initially the spring is on stretch, okay? To simplify this, to eliminate this confusion. All right, so let's speak on the problem. So whatever you want, guys, you can select, okay? Instead of me, yes. The problem of what? You want another spring?
Yes.
Maybe let's do this one, see if you can do it in both ways. Didn't we do this one or something similar already?
Yeah.
Yes, we did.
Yeah.
Because this one is one that you can really do using kinetics and the stuff. The other one we did as well, but it gets a lot more complicated. This one, what is the one? I'm trying to see, I mean, I looked at the ones that I like. Oh, this water coaster over here. Okay, so. All right, so what about that one kind of looks similar, no? But I'm trying to do 1565. I think it's probably about the same, I'm guessing, just by looking at the figure. Let's look at 1565. Do the figure or do the figure? 1565, yeah. It's another one with a spring, no? Yeah, I don't know. Yes. I'm just doing the quantity. I see a spring, that's all. Okay, good. The spring is on stretch, no? I like that one.
I'm stretched. It's.
No, but when it's at 2, I guess, no? The spring is on stretch when the core is in position 2. So now if that one was compressed or stretched, then it was going to be different, no? All right, so. I mean, I think this one, since we did the other one, should be straightforward. I mean, I don't know what we need to solve for, but. My figure is not good at all, but what can we do? 2, 1. So good thing is that, let's see, the color is 4 kilograms. Initially at rest, so that means V initial equal to 0. The velocity, so its velocity when he has fallen to position 2 is, okay, so 4 meters per second. The spring is on stretch when the core is in position 2. What is the spring constant K? I mean, that one. I mean, this 1563, 65. No, okay. Well, we do that one, okay? And we know the distance is 250 and 200. So I put 0.25 meters and 0.20. Okay, so what about you try to do it by yourself, no? This one has no trick that I can see, okay? At all. Straightforward. So I'll give you another 7 minutes. Should be plenty of time. Okay, so let me just show the solution of this. 1565 for the video. Okay, so let me go. We have 12 minutes, so let's go to the book. So there's problems that actually you can solve them in 3 different ways. Let's see if there is one of them. Oh, this? Okay. I think at the beginning of semester, we did derive the equation for the parabolic motion. We did, huh? So. I mean, I'm trying to find something that has 2 blocks sliding. That looks like the beginning of the semester. Oh, this kind of stuff. I mean, this one will be tricky. This one, I mean, 3 is too much. I mean, it's not really 3, it's 2 because this one is fixed. But I mean, probably we'll do a problem like this one. Okay, but not right away. These problems are good because really shows a good understanding. This one, for example, we could solve since you asked, can we solve this problem using kinetics? Yes. Can we solve this problem using work energy? Yes. But since somebody mentioned about here relative velocity. So what happened, for example, when this point here, so basically, let's say this moves 1 foot up, how much is B going to move relative to point A? It's moving 1 foot on the same direction plus 1 foot relative. Correct? So you see, so using kinetics, you might have to be careful. Using work energy, you can just say that it moves twice the distance, no?
What's the distance?
Because when this is moving 1 up, this one will be moving 1 down, but this will also be moving 1 up in the same direction. So it will be twice, no? Yeah, because of the sliding. Okay, but anyway, that's again, that would be to go for a complicated problem. Okay, this one would be a very simple problem. Maybe we shut down that one, or maybe we can do this one. This one, you could solve it in both ways. This one, you could be solved with kinetic. I don't know what you need to solve, okay, but I'm just looking at it. So, for example, if you use work energy, you don't cut the rope. But if you cut the rope, then what you're gonna have? You need to look at the tensions, no? How many? If you do this with kinetic, how many systems are you gonna have? 1, 2, and 3. Two if you assume that the pulley has a mass.
Right.
Okay. If they assume that probably here they say that it has no mass, it will not be. Okay. But you see, this could be solved both ways. This one, for example, is a little bit more complicated than this one, but it's kind of the same. So this problem, probably in all these problems, they assume that the pulley is with no mass. Okay, but a problem, for example, that I like to do with you in class, okay, is that imagine here that the pulley has a mass. So basically, we need to calculate the I of the pulley. Okay, and imagine that, let's say here is the ground. All right, so the ground is much higher than what is this is going to move. No, so let's say this one weighs twice the weight of this one. So when you release this one from rest, this is going to move. Whatever distance this is moving, this one is going to move up. But is it also going to move something more, or is that going to, or that's it? Because the pulley is still going to have some what? If you want to think about energy, the pulley is still going to have some energy additional, no? That might push this one a little bit higher before falling back. Yeah. So, for example, one problem that I can ask you here could be what? It's like how much more this block is really going to move with respect to this one, no? Yeah. Okay. Probably a problem, that I generally do. I don't have it here, but just to think about it, okay? So brainstorm it if you want. Well, it is for next week because next class, I'm going to try to finish the material of the class, okay? And then we can work just on problems. But I think a good problem for this would be, for example, let's say you have a pulley. Would be good if I find a problem like this one. And you have here a block that weight whatever. Let's say that weights 5, okay? And let's say you have another block that weights 10. Okay? Now imagine that I say system is initially at rest. Okay? This block is going to fall a distance h. Okay, how much is this block going to move? Okay, so if you neglect the effect of the pulley, then it's very simple. If this move h, this one's going to move h. But if you take into consideration the pulley, this one is going to move h plus whatever extra energy this is going to try to pull it, no? Yeah? Okay? So probably next lecture, I'm going to try to finish the material, or probably the next 2 lectures, we're going to try to finish the material. And after that, we're just gonna do this type of problems, okay, to really test your knowledge and how well you learn the material that within this semester. Is that okay? And again, start working on assignments. If you have problems that you are interested on us to work on, just let me know.